Namaste and a very good evening to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about how to build a time series model using SPSS. Even before I proceed to demonstrate how to build a time series model using SPSS, may I request you to subscribe to my channel, also like and share my videos. I've got two data sets in this video. The first is what is called as the training data set. In the training data set, as you can see, there are 5 important columns: serial number, date, year, we have month, and then we have wholesale price index of rice. The first row corresponds to January 2001. We have the wholesale price index of rice, which is 164.8. Then we have February 2001, wherein the wholesale price index of rice is 163.8. Then we have the information on March 2001, where the wholesale price index of rice is 165.10. Starting from January 2001, the last record in this data set would be April 2009, which means that in the training data set, we have 9 years of information about the wholesale price index of rice. Let me now show you the second data set that I will be using. This is the second data set which I have, which is called as the transposed_2. I'll be using this as the test data. I've got very similar variables as in the first 5, like year, month, date, rice, and light diesel oil. One very important difference here is that in this data, starting from January 2001, I have information all the way up to April 2010. My goal here would be to build a model on the training data set for 9 years, generate the predictions for the 10th year, compare the predicted values and the actual values for the 10th year, and make sure that the predictions are very close to the actual values. To do this, let me go back to the training data set. As you can see here, right now I'm working on the training data set. Using this data set, I will be creating a time series plot. Why? Simply because one of the most important prerequisites for us to build a time series model would be to examine whether or not there is stationarity in the data. This becomes an important prerequisite. How do we check whether there is stationarity in the data set or not? To check for the presence of stationarity, we can use a time series plot. Let me begin by creating a time series plot. I have clicked on the Analyze menu. I'll be selecting the option Forecasting. Here, I will select the sequence charts. Once I select the sequence charts, the dialog box for the sequence charts opens up. Under the variables list, you have rice, and in the x-axis, we have time axis labels. Once we have chosen these two variables, let me go ahead and select the OK button. This is the output window. In the output window, I'll be selecting the last option under the time series option. As we can clearly see here, in the x-axis, I have data from Jan 2001, May 2001, September 2001, all the way up to Jan 2009. What is clearly visible is that we have an increasing trend in the wholesale price index of rice. Because we have an increasing trend, we can conclude that the data is non-stationary. Remember, if there is a trend component or a seasonality component in the data, we can infer that the data is non-stationary. Theory says that when we speak about stationarity, there are three types of stationarity. Stationarity with respect to mean, stationarity with respect to variance, and thirdly, stationarity with respect to covariance. Only when the data is stationary with respect to mean, variance, and covariance can we claim that the overall series is stationary. So the first inference that I can draw from this particular graph is that the wholesale price index of rice is non-stationary. With this exploratory data analysis, I will be proceeding to create the first time series model. How do I create the first time series model? To create the first time series model, let me go to the SPSS icon. I will choose the training data. Right now, as you can clearly see, I am working on the training data. To build the first time series model, I will go to the Analyze menu, come to Forecasting option. Here, I'll select the second option, namely Create Traditional Models. Once I select this particular option, a new dialog box, which is called as the Time Series Modeler dialog box, opens up. In the left side, you can see 4 important variables. In the dependent list, I will be pushing the variable rice. What I'm effectively doing here is to build a time series model for the wholesale price index of rice. May I draw your attention to this particular box which says method is expert modeler feature, which means that SPSS itself will build the best fitting time series model for the wholesale price index of rice. As you can see here, I will select the option Save. In the Save option, I will be choosing predicted values, LCL, as well as UCL. These are the 3 options that I will be selecting. I have the Options tab here. There are 2 items, namely first case after end of estimation period through last case in active dataset. The second option here is first case after end of estimation period through a specified date. The year will be 2010. Why 2010? Because I will want to generate predictions for the next year. The month will be April, which I will indicate by specifying the number 4. Let me now go ahead and click on the OK button. As you can see here, this is the output of the expert modeler feature. As you can clearly see here, the expert modeler feature has built a ARIMA model with parameters 1, 1, 0. According to SPSS, this is the best fitting model. As you can see here, the table is the model summary table. This gives you a variety of statistics which tells me whether the model fits the data well or not. We have elements like stationary R-squared, root mean square error, MAPE value, max APE or maximum absolute percentage error. Then we have the mean absolute error and maximum absolute error. We also have the normalized BIC. What is a very popular way of assessing the model fit would be the MAPE value or the mean absolute percentage error. Typically, if the mean absolute percentage error is less than 5%, it indicates that the model is a good model. Let me scroll down here. Here, you can see what is called as the model statistics. A very important model statistic would be the Young box statistic. The Young box statistic value is 8.6. The degrees of freedom is 17. and the significance value here is 0.951. Because the p-value here is bigger than 0.05, I can go ahead and claim that the model fits the data well. The important question is, does it really fit the data well? And to answer this question, I'd like to look at the graph. As you can see here, the red line is the observed data. The observed data is present until May 2009. The blue line represents the forecasted values. What's very interesting here is that the observed data is clearly showing an increasing trend. However, the forecasted values shows that there will be no trend, and for the next year, we are getting a flat line here, which is a source of concern. This is where I'd like to draw your attention to a very important point. Merely because a software has suggested a model to be a good model, it need not necessarily be a good model. Unless the predicted values and the actual values are very close, we cannot claim that the model is a good model. What I'd like to do here is to go back to the training data set. As you can see here, there are 3 new columns that have been generated by SPSS. The first new column is the predicted value of rise. We have the LCL value of rise as well as the UCL value of rise. Let me copy the predicted value by selecting this particular column. I will right click and select copy option. After copying this, I'll go to the test data and paste it here in the last column. If we go ahead, right click and simply say paste, it takes a couple of moments to populate the wholesale price index of rice in the second file. I have successfully pasted the predicted wholesale price index of rice in the second file. Now, I will be comparing the actual values of rice with that of the predicted values of rice. To compare the actual and the predicted, I'll go to the Analyze menu, select the forecasting option, and here I will hit the sequence charts option. This will open up a new dialog box which is called as the sequence charts dialog box. Let me select the actual wholesale price index of rice, also the predicted wholesale price index of rice. In the time axis labels, I will be choosing the date variable. Let me go to this particular box which says timelines. This will open up a new dialog box. I'll select the second option, lines at each change of. I have to specify a reference variable. Either you can specify a reference variable or avoid this option and choose line at date. I want a vertical line at 2009 April. So I'm going to type here 2009 for the year field and the month will be 4. Let me now select continue and then click on OK. You can see here, this is the output of our analysis. It's a very interesting chart. You can see here in the x-axis, we have the time, and in the y-axis, we have the wholesale price index. You can clearly see that there are 2 lines. The first line is in blue color, and the second line, which is the predicted wholesale price index, which is indicated in red. Clearly, you can see up to May 2009, the red line and the blue line are very close to each other. Since the red line and the blue line are very close to each other, it means that in the building phase, the model has learned the characteristics very well. Our actual and the predicted are very close to each other. But the problem comes after May 2009. Clearly, you can see the blue line is climbing up, indicating that the actual wholesale price index of rice is increasing. However, the red line is not climbing up and tracing the path of the blue line. It's almost parallel to the x-axis. Since the red line and the blue line have a gap, it's a clear indication that the model does not perform satisfactorily for the next year. This is where there is a lot of scope for improvement of the model. Many times when we build the model for the first time, we tend to overlook certain things. This is where hyperparameter tuning of the model would help. This is a quick and a dirty model that I've built. I'd like to improve the performance of the time series model. To improve the performance of my time series model, let me go to the training dataset. As you can clearly see here, this is the training dataset that I have. In the training dataset, what I'd like to do now is to build my own customized model. I will not use the expert modeler feature that is present in SPSS. I'd like to specify my own parameters. How do I do that? I can go to the Analyze menu, come to the Forecasting option. The second option here is Create Traditional Models. Let me select Create Traditional Models option. This will open up the time series modeler option. You have the variables tab, which shows you all the variables that are present. Once you have all these variables, may I draw your attention to the method of building the model. Earlier, I had selected the expert modeler feature. Here, when I click on the drop-down menu, you can also select exponential smoothing and ARIMA option. In the drop-down menu, let me select ARIMA model. ARIMA stands for Auto-Regressive Integrated Moving Average. You can specify the parameters of the model by clicking on the criteria box. The criteria box gives me different options. You can see here, this is the structure of the ARIMA model. You have the PDQ parameters or the auto-regressive differencing moving average option. You can specify the non-seasonal parameters or the seasonal parameters. I've experimented with different values for PDQ, and I have come to the conclusion that for this data, when the P value is 2, the D value is 1, and the Q value is 3, we get the best model. What this does is, this will build a ARIMA model with seasonal parameters, or in other words, this will build a SARIMA model. A SARIMA model stands for Seasonal Auto-Regressive Integrated Moving Average, with parameters being 2, 1, and 3. We can go ahead and click on Continue and then hit the OK button. As you can see here, the SARIMA model that I have built has generated the predicted values, LCL, as well as the UCL values. Initially, there are a few blank entries, but as I scroll down, you can see there are predicted values based on the SARIMA model. Let's go ahead and examine the graph of the prediction. This is the output window. You can see the model type. The parameters here would be 2, 1, and 3. Let me go ahead and select the chart option. As you can clearly see here, the red line is the observed line, and the blue line here would be the predicted value. The blue line is very promising. It looks a lot better than the earlier model predictions that we had generated through the expert modeler feature. Let me show you the earlier graph that we had obtained. This is the series chart. You can see here, after May 2009, we had a flat line indicating that the wholesale price index of rice would not increase, it would remain constant. The series chart now indicates that the wholesale price index of rice would increase. But how do we know whether this is believable or not? To answer that question, what I will be doing is, I'll go back to the training data. In the training data, you can see the predicted values based on the SARIMA model. Let me select the predictions, right-click, choose copy. I will now come to the test data and paste the predictions obtained from the SARIMA model. So this is the predicted values based on SARIMA, and this would be the predicted values based on ARIMA model. My goal here would be to compare the prediction of the SARIMA model with that of the actual values for rice. How do we do this? We can go to Analyze, Forecasting. Here, I will move to Sequence Charts option. This will open up a new dialog box, which is called as the Sequence Charts dialog box. Let me remove the earlier prediction. I will be now selecting the predictions based on the current model or the SARIMA model. Let me go ahead and hit the OK button. This is the output window of SPSS. Let me now go to the time series predictions. Very interesting graph. In the x-axis, you can clearly see the time variable. You have two lines. One is the blue line. The second one is the red line. Since the red line and the blue line are very close to each other, we can say that the model predictions are quite good. What's very interesting here is the future forecast post May 2009. In future, when you look at the prediction for the wholesale price index, please observe the blue line and the red line. There is a small gap, but nevertheless, the red line is tracing the path of the blue line, which means that now the predictions that have been generated through the SARIMA model are very close to the actual wholesale price index of rice. This is where we can say that the SARIMA model that we have built is a lot better than the ARIMA model that was built by the expert modeler feature of SPSS. Let me now show you the earlier time series plot. This is the earlier time series plot that we had got. Clearly, the red line is not climbing up, and hence the predictions of ARIMA are not as good. Let me show you the current time series plot. You can clearly see the blue line and the red line are very close to each other, indicating that the predictions are quite promising. Question is, can we further fine-tune this particular model? This is where our skills in feature engineering will be tested. To further fine-tune the performance of the model, what I will do is I'll go back to the transposed file. In this data set, I will be building a ARIMAX model. I will be using the independent variable. What is the independent variable that I can use? You can see here, there is a very useful variable, namely the light diesel oil variable. Light diesel oil influences the wholesale price index of rice. When we talk about interstate transportation of rice, many times you have trucks and large vehicles which facilitate transporting of rice from one state to another. And if the government of India increases the price of light diesel, that will influence the price of rice as well. So increasing the price of petrol or diesel usually has an impact on the wholesale price index of rice. To check whether there is correlation between light diesel oil and rice, what I will be doing is I will be creating a correlation plot. How do I do this? Let me go to the Analyze menu. Here I will select the forecasting option. I'll move to the option cross correlations. Once I select the cross correlations button, a new dialog box called as cross correlations dialog box comes up. In the left side, you can see variables like rice and some of the other variables that are present in the data set. Let me select rice and light diesel oil. If you want, we can perform transformation like natural log transformation, differencing, and seasonally difference as well. I'll avoid all these things and simply click on OK. So this is the output of the cross correlation function. Let me scroll down. You can see here, this is the table for cross correlation. You have the lag values. You also have the lead values. What's very interesting here is that the correlation values are quite appreciable. It is 0.798 when the lag is 0. When the lag is -1, it is 0.786. When the lag value is -2, the cross correlation value is 0.778. Usually, if the correlation value is greater than 0.7, we say that the correlation is strong, which is what we are seeing in the second column. So this is the cross correlation value with that of light diesel oil. You can also see the CCF plot for rice with light diesel oil. If we come back to the data, what I'll do now is to create lag variables for rice as well as light diesel oil. To create the lag variables, what I can do is go to the transform menu. You have the option called create time series. I'll have to create two new variables here. Let me select the option create time series. This will open up a new dialog box, which is called as create time series. What I'm going to do is select the variable rice. By default, SPSS says that it wants to difference because the function here is difference. Let me click on the drop-down menu and choose lag. If we go ahead and change this, what this does is it would create a lagged variable for rise. I'm going to create the lag variable for rise and use that as the independent variable for predicting the wholesale price index of rise. Not just rise, I also want to use the variable light diesel oil, but I will make sure that the lag of order 1 is selected. In fact, now you can see lag of light diesel oil is automatically appearing, which means that SPSS has understood that I would like to create the lagged variable for rise as well as light diesel oil. What is the meaning of lag in this context? The lag variable here indicates that last month's price of wholesale, last month's price for rise will influence the current month wholesale price index of rise. Similarly, if you increase the light diesel oil for the last month, you may see the effect not immediately, but after 1 month. And therefore, we are creating a lag variable to indicate that the wholesale price index of rise for the last month, as well as the wholesale price index of light diesel oil for the last month, both of these will influence the wholesale price index of rise for the current month. With these specifications, let me go ahead and select the OK button. You can see here, this is the output window. SPSS tells me that it has created two variables, namely rise and light diesel oil. When we go back to the data, you can see here, there are two new variables here, rise _1 and light diesel oil _1. I'm going to use both of these variables to build a ARIMAX model. But hang on, there is a problem. The problem is that to build a ARIMAX model, I'll have to get rid of these missing cases. So let me select the first row and simply clear the missing cases. Let me go to the last column. You can see here the missing cases have been removed. Let me now show you in the third phase, how do we build a ARIMAX model. I'll go to Analyze, Forecasting option. Here I'll choose Create Traditional Models. This will open up a new dialog box. In this dialog box, you can see the variables to the left side. You can also see the dependent as well as the independent variable. Let me select the variable rise and push this into the dependent variables list. Under the independent variables list, I will be choosing the lagged variable for rise as well as the lagged variable for diesel oil. As you can see here, for the first time in this video, I have introduced the independent variables. Earlier, I had not specified the independent variables. Therefore, it was just a ARIMA model. Now that I'm specifying the independent variables, this model is called as the ARIMAX model. Let me go to the expert modeler feature. I don't want to use the expert modeler feature. I'll be using the ARIMA model. I have to specify the criteria here. So let me click on the criteria box. You are familiar with this particular dialog box. This is the ARIMA criteria dialog box, which allows me to specify the non-seasonal parameters as well as the seasonal parameters. When it comes to the seasonal parameters, I'll specify this as 2 for P. I will specify 1 for D, and I'll specify 3 for Q. So the seasonal parameters here would be 2, 1, and 3. Let me click on Continue. Now I'll select the button Save. I want the predicted values, LCL, as well as the UCL. The last of the options here is the options tab. I have to specify the end date. The end date would be 2010 and the month would be April. This will generate the predictions till April 2010. So this is our third attempt of building the best time series model that we can. If we go ahead and hit the OK button. Fantastic. You can see here the ARIMA model with 213 parameters have been generated. You can clearly see here the predictions for the ARIMAX model is being shown. Now, how do we know whether this ARIMAX model is good or bad? To do this, if we go to the Analyze menu, I'll be selecting Forecasting option. Here, let me select Sequence Charts. This will open up a new dialog box, which is called as the Sequence Charts dialog box. This will show you the variables list. Let me remove the predicted values for SARIMA and choose the predicted values for the ARIMAX model that we have built. The rest of the things will be as it is. Now let me go ahead and click on OK. The output is ready. Let me now look at the time series plot. So this is how our predictions look now. Very, very good model. You can see here the blue line and the red line are very, very close to each other, which means that the actual values as well as the predicted values are very close to each other. And what is really interesting here is the blue line and the red line post June 2009 are very close to each other, indicating that the predictions are very close to the actual values. The earlier gap that we saw between the actual and the predicted values have been reduced to a large extent. And therefore, out of the 3 iterations that we did, the first one was the expert modeler, second one was the ARIMA model, the third one was the ARIMAX model. We can go ahead and say that the ARIMAX model is the best out of the lot. Let me show you the earlier few graphs that I had generated. This is the first graph for the expert modeler feature. The forecasted values had a big gap. This is not a good model at all. Let me show you what I did in the second attempt. This is the output of the SARIMA model, a lot better than the expert model. However, still not good enough. The latest model that I have built would be, let me show you quickly. This is the time series plot for ARIMAX. This is a very, very interesting and cool stuff. As you can see, this is the best out of the lot. With this, I have come to the end of today's video. In today's video, you've seen 3 different approaches towards building a model, a time series model, a simple expert modeler feature. Second one is the SARIMA model, and the third one would be the ARIMAX model. I request you to subscribe to my channel, also like and share my videos. Thank you very much for watching this particular video. Have a great day ahead.